Hey, physics. I'm going to do the hanging Einstein practicum, the half Atwood's practicum here, so that you can look at the solution, how to do that, and check that against what you submitted. Let me show you what I got I got a Google Doc prepped up here that looks like this. Mr. McGrath, half Atwood practicum. I copied and pasted the things that are supposed to be in the Google Doc from Classroom here. So a data table that shows their position and velocity data. I don't have that yet. And then a graph of velocity versus time. So this is just like what you did in the fan cart lab, except you only have to do it once instead of the 5 times. And then the part here, let me put a space in there. So insert stuff there. 2 force diagrams for the glider and for Einstein. You can paste in your photos, which I did here. So I knew what those force diagrams were going to look like already. So I didn't have to wait till I did the other part. So I got that in here already. The mass of the Einstein holding onto the 60 gram, that's an N there, sorry, it's messy. I know that, well, I don't know what the mass is. So there's a couple ways you could deal with this. If you're thinking about, well, what about the 0.06 kilograms that he's holding on to? I'm just ignoring that for now, and I'm going to find out what the total hanging mass is. And then if I want to know what the mass of the doll is, I just have to subtract off the extra stuff that he's holding. That's how I'm going to treat that. You could make the mass of Einstein M and then have like M plus 0.06. I think that makes it, well, I know that that makes the algebra a little bit more complicated. So I'm going to treat it like this. What's the mass of all the hanging stuff? I don't know. I'm just going to call it small m. So then my force diagram would look like this. The force of gravity, of course, to find force of gravity, you take whatever that mass is and multiply by 10. So this is just 10m because I don't know what m is, but I do know basic algebra. So 10m. And then force of tension here is losing to that. On the glider, I've got the mass in kilograms is 0.44. So I'd have 4.4 newtons of gravity and 4.4 newtons of normal force. And then the tension pulling it off to the side here. So I also know that my Newton's second law equation, if I use the method of just finding the totals, the total for a half Atwood's machine is just the force of gravity on the hanging one. So that's 10m because, as you can see, these cancel out. And I should have put 2 little tick marks on this and this. Those balance out and the 2 tension forces cancel out. So this is the total unbalanced force right there. And then the mass total is 0.44 plus whatever m is, right? That's the 0.44 plus whatever m is. And then times acceleration. So what we need to do now is find the acceleration. So I need some data. Let's see, I'm going to need this. And let's see what will be an easy part to measure from. I guess it's just the very front edge of the cart. That looks pretty good right there. And I need a stopwatch. And I'm going to need to advance this. Oh, that's pretty early in the video. Let's see if we can get it just where we want. That's either one of those frames would probably do okay. I'm going to take that one. I can definitely see that it's been cut. Okay, so I'm going to 0 my timer and I'm going to make a data table. I'm just going to write this stuff down first. I don't know how many points I'm going to take, probably about maybe 10 or so. So time 0, position 0. I'm going to convert all my positions to meters as I go. So let's see what time interval seems like it'll be good for us. How about we do tenths of a second. Now it looks like it's gone about 1 centimeter. So that's 0.01 after 0.1 seconds. 0.2, I'm just filling out the time part of my table, my handwritten table here. I'm writing 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and go up to 1 second. That should be plenty of data there. So then I need to go up to 0.2 seconds. Oh, and I might not get that far, right? We'll see how far I get for, because as soon as Einstein hits his butt on the table here, it's over, right? As far as I can go. So maybe we'll see if those time intervals work for me. I didn't really think about that. That looks like about 5 centimeters. We'll call that 0.05. Then we'll go to 0.3. That looks like about 12 centimeters. 0.12. And oh boy, we're not going to get, let's see if we can even get 6 data points. We might have to go back and fill in some more data points. 0.21. And let's see if we can get to 0.5 without him hitting his butt. Oh boy. I think we're good there. I'm trying to see if he like hit and then bounced, but I think we're good. So that's the last one we'll be able to get, 0.5, and the glider is at like 33 centimeters, 0.33. I'm going to go back and get the points that are halfway in between those, because I would like to have some more points, more data. So I'm going to try to get 0.05 and see where it's at. Looks like it's maybe like half a centimeter, 0.005. And then at 0.15, oh dear, can't move the glider. Just kidding. I grabbed the wrong thing there. That looks like 3 centimeters, 0.03. And then at 0.25, we are at 8 centimeters, 0.08. And then at 0.35, if you're thinking like, does this really matter, like what time intervals you use? No, you just should be consistent with your increments of time. But if you did something different than this, should be okay. I just have to be consistent. That looks like about 16 centimeters, 0.16. And 0.45 is the last one that I need. That's at right in between 25 and 26. 26 and 27, sorry. At 0.265, I'm going to call that. Okay, I'm going to go to graphical analysis and got a new experiment here ready to go. I would like to do time here in seconds. And I would like to do position here in meters. And I know that in a second here, I'm going to do velocity also. Let's do that now. Velocity in second. Okay. Up a little bit. Looks good. And my times are, I got 0, 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, 0.5, 0.4, 0.45. And then my positions, which I just collected, are 0, 0.005, 0.01, 0.03, 0.05, 0.08, 0.12, 0.6, 0.21, 0.265, and 0.3. All right, that looks like what we would expect, right? Nice parabola shape bending upward like that. To get the velocity data, I need to turn on the tangent thing here. Again, if you didn't know about that feature, what I'm doing here, what the computer's doing is the same as finding the slope between this point and this point. So if you did 0.01 minus 0 over 0.1 minus 0, that would find the slope here. It's exactly what the computer is doing also. But I learned about this. So I'm going to use it. So 0.16 that looks like in that box. And then 0.26, 0.39, 0.52, 0.68, 0.80, 0.91, 0.04, 0.15, and 1.24. Right. Oops. Nope. Just kidding. I don't want to do the very last one. I want to do just the ones where I have a point on either side. So I'm going to leave the very first one and the very last one blank. Okay. So I'm going to go back to my Google Doc and check in with my physics teacher's instructions and see if I am doing the right things here. So I want a data table that shows position and velocity versus time. And I want a graph of velocity versus time. So I think that if I take this and turn this into a graph of velocity versus time, and I think I want a line of best fit. Let's get rid of that thing. Apply curve fit. A line of best fit. I'd like to see the origin in here, and it looks like I don't quite have that. I could double check anyway, even if I thought it was. It's close, but make that 0. And this, going to just scooch this down a little bit. This is the graph that we want, and I've got my data table here also. So I'm going to just snip this. All right, that looks good. So let's see, data table and the graph. That's all that. And the physics teacher person didn't say exactly to do this, but I'm going to go ahead and do my equation here, which would be velocity. That's what I'm on my y-axis here. And let's blow this up. Font equation. Velocity is equal to, you know what? I think I'm going to go and do this as an equation too, because that will look nicer. Velocity equals 2.54 by slope. And units of rise, meters per second, over seconds times out of my equation there. Acceleration. And then there's an intercept here. It should be 0, right? Because the initial velocity should be 0, but I'll just write down what it has, or type in what it has here, 0.02. The units for an intercept would be y-axis. Okay? And then the meaning, the slope for every 1 second passes, the velocity increases by 2.54 meters per second. This is the acceleration. You know what? There's an exclamation point. Okay, so I got my force diagrams. Here they are. And there's my Newton's second law equation. So now I can, in this equation, I've got my 2.54. So I've got a number here now, 2.54. All right. We'll do some algebra now on the computer. So there's my 10m is equal to, now I need to distribute the 2.54 in here. So grab my calculator. 2.54 times 0.44. That gives me here 1 point. I'm going to round it to 1.12 plus 2.54 m, right? It's distributing that. And then more basic algebra 1. Subtract this over the other side, which is going to give me 7.46 m. Right, that's just 10 minus 2.54 is equal to 1.12. And then last, I'm going to, I want that capitalized very much. 1.12 divided by 7.46 is 0.150. That's going to be in kilograms. Okay. Now, this is the total hanging mass. So the mass of the doll, the Einstein doll, is 0.150 kilograms minus the stuff that he's holding on to, which is 60 grams or 0.06. I hope that makes sense to you. So the mass is 0.09 kilograms. Or convert it back to grams because that's how things were given. And that's pretty close. That would be certainly good for 100. The actual mass of the Einstein doll, it's just about 100 grams. So I'm just about 10% off. And, considering how we're collecting data and stuff, it's pretty good. So there you go. That's how to do it. And if you have any questions about your grade, then you shoot me an email and we can discuss. Okay, thank you.